Reference angle definitions. We would like to take our trig functions and broaden the definition so that we can put in any angle, not just angles in right triangles. How can we get a ratio to come out no matter what angle we stick in? Well, that's where the reference angle definitions come in. Well, here's how it works. Take any angle you want, go to the XY plane, and draw that angle in standard position. Here's an example angle I can use. Next, identify any point on the terminal side of that angle. Here's a point. I'll label its coordinates x, y. Then from that point, drop a perpendicular down to the x-axis. It must be the x-axis, the x-axis. Now fill in the side lengths of the triangle. If the coordinates of this point are x, y, then this distance here must be x. It's a positive distance because I'm in the first quadrant. And this distance here must be y, over x, up y, to get to the point x, y. I will also call the distance from the origin to the point on the terminal side r. R is a true distance, not a coordinate, so r is always positive. Okay, let's write down our definitions. The sine function returns you the ratio y over r. The cosine function, x over r, and the tangent function, y over x. Here's the great part. These definitions are completely connected to our former definitions, to SOHCAHTOA. Take a look at the picture. You have sine is y, the opposite, over r, the hypotenuse, SOH. You have cosine is x, the adjacent, over r, the hypotenuse. You have tangent is opposite y over adjacent x. So these definitions remain true to our former definition while broadening it out to allow for any angle to be inserted into the functions. The other three functions are still the reciprocals of the first three, so cosecant would be r over y, secant r over x, and cotangent would be x over y. Again, the key here is that SOHCAHTOA still works. Now, things get a little trickier if we don't land in the first quadrant. Let's take a look. Suppose I had an angle that's bigger than pi over 2, bigger than 90 degrees. Maybe it lands here in the second quadrant. Well, I'm still going to follow those same steps. Draw my angle in standard position, mark a point on the terminal side, drop a perpendicular to the x-axis, always the x-axis. When I do that, I form every time this right triangle. Now notice this time the angle theta is not inside that triangle. Instead, the angle inside the triangle is this angle. Well, that angle has a name. It's called the reference angle. The reference angle is the acute angle between the terminal side and the x-axis. That's exactly what I've drawn here. The acute angle between the terminal side here and the x-axis. So we call that the reference angle, and we call the triangle the reference triangle. Let's continue with our steps. I've dropped the perpendicular. I've identified a point here. I'll call it once again x, y. Now I'm to label my sides. Well, when you're outside the first quadrant, you just have to be careful. Yes, it is still true that this is length x and this is length y, but since I'm in the second quadrant, that x coordinate there, that's going to be a negative number, and that will impact my answers when we start working out the examples. The y is still an upward direction, so the y would still be a positive number. R, remember, is a true distance. No matter what quadrant you're in, r is always positive. So when you're outside the first quadrant, you do have to pay attention to the signs, remembering that r, of course, would always be positive. The best news here is that SOHCAHTOA still works as long as you use it in regards to the reference angle. Here's those same definitions. It's the same definitions we just wrote down. Sine theta is opposite y over hypotenuse r, opposite over hypotenuse. Cosine theta, x over r. Well, with regard to the reference angle, adjacent over hypotenuse. Tangent, y over x, opposite over adjacent. The reference angle definitions allow us to still use SOHCAHTOA no matter how big or small the angle is or what quadrant we are working in. Okay, let's look at an example. So this one says, find the 6 trig functions of angle alpha if the point 1 comma negative 3 lies on its terminal side. Let's see, the point 1, so that would be over 1 and down 3, so somewhere around here. Here's the point 1 comma negative 3. The terminal side of my angle goes through that point. Of course, my initial side is always here. Here's angle alpha. I should say maybe there's angle alpha. Maybe angle alpha spun around 5 times before it landed there. Maybe angle alpha is a negative angle. I'm not exactly sure. It really doesn't matter because all that matters is knowing something about a point on the terminal side. I've got my angle in standard position. I've got a point on the terminal side. I'm going to drop. Now, when you're below the x-axis, dropping actually means going upward. So I'm going to go up to the x-axis, forming that perpendicular. Forming my reference angle would be right here. Here's my little reference angle. And my reference triangle is that triangle. Well, let's see. Let's fill in some side lengths. This is the point 1, negative 3. So obviously, this side has length 1. And you could say this side has length 3, but since I'm in the 4th quadrant, we know that 3 is actually a negative 3. It's the coordinates that matter. So right 1, that's a positive number. Down 3, that's a negative number. What about the r? Well, I'm going to have to calculate it, and of course I can by simply using the Pythagorean theorem. A squared plus b squared equals c squared. That's 1 plus 9 equals c squared. C squared is 10, which obviously means c is the square root of 10. Remember that the r value is always positive, no matter what quadrant you're in. It is a true distance. Well, once I have the 3 sides labeled, all I have to do now is use SOHCAHTOA. I can, of course, refer over to these definitions if I want to, but I don't really need to. I can just use SOHCAHTOA by referring to the reference angle. So let's start writing some of these things down. For sine alpha, I have opposite negative 3 over hypotenuse square root of 10. I'm using the reference angle to find my opposite, to find my adjacent. Right? This would be the opposite. This would be the adjacent. This would be the hypotenuse. I need to rationalize the denominator here. So I get negative 3 root 10 over 10. For cosine, let's see, adjacent over hypotenuse. Again, I'll have to rationalize. Square root of 10 over 10. Tangent alpha, let's see, opposite, negative 3 over adjacent 1. That simplifies to be just negative 3. By the way, a word about the negatives. Probably the best way to write a negative fraction is to have the negative on the side. A negative on the top is fine, but this is probably best. So we have our answers to the big 3. I could have used the definitions over here, y over r, x over r, y over x. That would have been just fine, but I don't really have to. With a great picture, I can just use SOHCAHTOA. We can write down the other 3 quickly. They're just the reciprocals of the first 3. Cosecant would be the reciprocal of sine. Remember, it's easier to use the unrationalized version. If I flip that thing upside down, I'm just going to get negative root 10 over 3. For secant, if I flip over the unrationalized version, I will get square root of 10 over 1, which simplifies, of course, to just square root of 10. And for cotangent, the reciprocal of negative 3 over 1 would be negative 1 over 3. And so there's my other 3 ratios. We now have all 6 trig ratios for angle alpha. Again, the moral of the story, whether your angle is in degrees or radians, whether it's negative or positive, whether it's big or small, as long as you can find a point on the terminal side, you can write down the 6 trig ratios. Thanks for watching.